Hi, so the book's description of assaying a coin, finding a coin density, kind of bugged me a little bit, so I want to run through that. Yeah, so the idea is that you drop a coin into water and you weigh the coin first, and then you use this buoyancy force to estimate the density of the coin. So then you can tell if the coin is pure metal or some other mixture of metal. So so you've got a balance here, and the coin's going to be more dense than water, and so the book uses the term apparent weight, which is kind of strange. What they mean is the net force um, in the downward direction. Fine. So if that's what you mean, you should probably say it. So the net force then is just going to be the sum of the forces. So if since positive is down for weight, then the weight is the positive quantity, and then it's lessened a bit by the buoyancy force, like that. So that's what the book is using, and what actual assayers will use to estimate the purity of a metal. Historically, gold. At the gold rush days, you'd go and get your gold assayed, and they'd tell you how pure it was. A net force or apparent weight. I mean, you could make up a symbol. So I'm just going to make up a symbol to mean apparent mass. So if you stick a coin in water and then weigh it while it's in water, then it will, because of the buoyancy force, appear to weigh a little bit less. And so I'll just call that apparent mass m prime. So I can rewrite this equation. Net force is apparent mass times the acceleration due to gravity, and that's going to be weight, which is mass times the acceleration due to gravity, minus uh, the buoyancy force, which was the volume displaced by the coin times the density of water. Remember, that's kind of mixed up there, times the acceleration due to gravity. And of course, you can divide those g's out if you want to. So your apparent mass is the actual mass of the coin minus volume times the density of water. So that's not a huge, hairy, scary equation. The this mass could be rewritten if you wanted to, and I think we probably do, in terms of the density of the coin itself. So it's the volume of the coin times the density of the coin minus the volume times the density of water. And that's what might be of interest when you are doing this problem. So the mass, or the density of the coin is the thing to solve for. So we'll solve for that. So we add to both sides. So we have an apparent mass plus the volume times the density of water. Then we got to divide by V, and that's equal to the density of the coin, which is usually the result that you want. You're going to measure the apparent mass of the coin. You'll really measure the apparent weight, but then you'll divide by that g to get the apparent mass. And then you will have measured the volume displaced of the coin, and you know the density of the water. So this is maybe something that's a little more systematic than what the book gave you to solve all those types of problems.